This directed graph displays a network of 5 nodes, and our goal is to find all the valid cycles hidden inside it. To do this systematically, we need to track 4 state variables: our current path, our starting vertex, the next target vertex, and an absolute length bound, which we have set to k equals 4. We begin with a depth-first search. Starting at node A, we move along the outgoing edges to B and then to C. With each step, the algorithm updates our active path array to record the nodes we are currently visiting. From C, the algorithm evaluates the next possible step. It looks at the outgoing edge pointing to A and checks that target against our variables. The next vertex is A, and our start vertex is also A. Because the target matches the start, the search has successfully closed a loop. We have our first valid cycle, establishing the baseline requirement for our search. A path must return exactly to where it began. To find remaining cycles, the algorithm backtracks to B, branching down a new route through D and E. Our path is A, B, D, E. Node E points to D, but D is already active in our path. Stepping forward crosses our own path. To prevent the search from getting trapped in an endless loop, Johnson's algorithm uses a dedicated data structure. As seen in the code, a Boolean array tracks blocked vertices. When a node enters the stack, its blocked status becomes true, explicitly forbidding revisiting it. With D blocked, the search redirects to the other edge from E, pointing back to A. The target matches the start, logging a new length 4 cycle. By strictly rejecting active vertices, every recorded cycle remains simple, defending against infinite, repeating loops. Clearing the path, we backtrack to A, advancing down a new branch, A, D, E. As the algorithm evaluates the edge from E back to D, what happens? D is already active and rejected. The search pivots to A, logging a length 3 cycle, initiating one final traversal, A, B, C, E. The path contains 4 nodes, hitting our absolute limit of k equals 4. Evaluating the next edge to D, it calculates a length of 5. The edge is immediately rejected based on the k-bound. This preemptive truncation is mathematically necessary. Bounding the search scope aggressively prunes dead-end paths. This prevents computational time from growing exponentially in massive graphs, maintaining an efficient worst-case execution time proportional to nodes, edges, and valid cycles. There is one final complication known as cycle isomorphism. Look at our first cycle, starting at A. If a search later initiates from node B, it will find B, C, A, B. A search from C will find C, A, B, C. Without intervention, a standard search algorithm reports these as 3 distinct outputs, even though they represent the exact same geographic loop in the graph. We eliminate these duplicates by enforcing a canonical starting vertex. By assigning an integer ID to each node and forcing the search to only report cycles that begin with the lowest ID in the path, the redundant rotations are filtered out automatically. Let's review the rule set. We required the path to return to its cert. We blocked active nodes to ensure simplicity. We truncated the depth to respect the maximum length bound. And we required a canonical starting vertex to prevent duplicates. Layering these rigid mathematical constraints together takes a potentially infinite chaotic graph traversal and turns it into a precise, targeted extraction tool.